Yeah, but here it's like the it worked. Okay, sweet. Can we all hear me now? Yay. Okay, sweet. Sorry, guys. Okay, well then I guess I'll start completely over for those of you at home. All right. Yeah, not really. Okay, so basically, um, actually, I won't have to start over because the screencastify had access to my microphone. So in the video, it'll all be there. So just go ahead and watch the first couple minutes of the video and you'll kind of get everything that I just said. Okay, so let's go ahead and move on to the definition of a limit. Right? Again, this is one of those kind of mathy definitions that we don't like, right? But this one, there really isn't some really nice, concise, easier way of saying it. So you might as well just go ahead and write it down. But it says if f of x, which of course f of x is just our y, right, becomes arbitrarily close to a unique number L as x approaches some number c, right? They call it c just because it can be any number. It doesn't have to be the same number each time. All right, from either side, then the limit of f of x as x approaches c is L, right? And basically, down here at the bottom, this is the notation that you'll see. And this actually is a typo. This 0 here. All right, this C down here, or this 0 down here at the bottom. Let me get a pen. All right, this should not be 0. This should be the letter C. All right, so this is how you'll see it written mathematically. All right, and it'll just say, right, the limit as x approaches C, that's what this notation means right here, of f of x is equal to L. And again, of course, L is just some number. And C is just some number as well. So that is our definition of a limit. Okay, so it says use a table to estimate the limit numerically. Okay, so what they say when they talk about using a table, let's see if I can move this stuff up here. All right, so we're going to be using a table. So we're doing the limit as x approaches 0. Okay, so we're going to have some x, and we're going to have our f of x, which of course is just our y. All right, now it says as x approaches 0, and if you remember from that definition that we just wrote down, right, it said from both sides. Okay, so we're going to have to approach 0 from both sides. Well, basically what that means is we need to put 0 here in the middle. All right, first we'll talk about approaching 0 from the left. All right, think about a number line. What number is just to the left of 0? -1. So let's start with -1 over here. All right, and then I want to get closer to 0. Let's say maybe -1/2. All right, I want to get closer to 0. Maybe -0.1. Closer to 0 yet. Maybe -0.01. Right? And at that point, I'm pretty close to 0, right? Very, very close. Could we get closer? Sure. Do you have to pick these exact numbers? No. All right, as long as you keep getting closer to 0 from the left and you end up being very, very close to 0, you're going to be okay. All right. Similarly, we can go from the right side as well. Again, on a number line, what is just to the right of 0? 1. So we can start at 1 over here. All right, I want to get closer to 0. I'll just kind of mirror the other side here. This really only works, the mirroring, when you are dealing with 0, so do keep that in mind. All right, so of course 0.5 is closer to 0. All right, then 0.1 is closer to 0. 0.01 is even closer yet to 0. All right, so we have x over the square root of x plus 1, all minus 1. All right, so somebody will have to remind me of this at some point. Actually, I can write it down here. All right, because obviously we're going to want to use a calculator to get these values, correct? All right, so there's a couple of ways that we can do this. All right, so if we pull up a handy-dandy calculator, so of course we were first starting with -1, right? So of course we can alpha y equals gets us our fraction command. In the numerator we had x, well, but of course I'm not putting in x, right? I'm putting in -1. All right, and then down below we have the square root of x, which in this case is -1, plus 1, and then outside of that, -1. All right, so we go ahead and hit enter, and we get 1. So we come back here, we can put 1 right here in my table. All right, now, do I really want to take the time to go through and retype this in every single time with every one of those numbers? No. All right, there's a couple of ways that we can kind of go a little bit quicker than retyping in everything manually. All right, one, and I'm sure most of you are familiar with this command on the calculator, at least I hope. If you hit second enter, it just brings up exactly what you just typed in last. All right, so then of course you could go through and just change things, right? So we would want this to be 0.5, -0.5. All right, so if I do 0, now of course it overtypes things when you do that, right? So if you have something that has more digits than what you typed in before, if you actually hit second delete, it will actually insert, so it won't overwrite things. So here -0.5 would work there. And of course we can go up here and do the same thing, 0.5. All right, so now we have -0.5 plugged in for x. We hit enter. All right, so 1.7071 roughly. 3 decimals is significant enough for there. All right, but again, even if we hit second enter here, this one isn't bad. I can just go back and change these to ones, whatever. Okay, there's actually even a much faster way yet, all right, to do this. All right, so what I recommend is you go to y equals, all right, we plug in our f of x, all right, so we're going to have x over the square root of x plus 1, and then outside of that, square root minus 1. All right. So now, if you go to second table, or second graph rather, it will take you to this table. All right. Well, that's all well and good, but this only has whole numbers, right? We did want -1, which we already have on there. We also wanted +1, so 2.412. Right, so I do know that this is going to be 2.412. Right. What's that? Why is it 412? I thought it was 414. Oh, my bad. It's 4142. That is correct. So, yeah, of course. I was just making sure you were paying attention. So 4, 2. Okay. What's that? Who, what, where? Still trying to, right? Okay. So, but still, that's not all that entertaining. All right. Well, I don't know if any of your teachers ever taught you this, but I certainly will. You definitely don't want to teach kids this too early because then it makes a lot of like algebra 1 and stuff super easy. But if you hit second window, it'll take you to this table set. All right. So you can kind of set up your table how you want. If you scroll down here to the independent variable, which variable is the independent variable? X, all right? So if you hit this to ask, basically that tells your calculator to ask you what X you want to plug in, all right? So now when you go back to your table, if it's the first time you've ever done it, your calculator will bring it up blank like this, right? If it's not the first time you've ever done it, then there'll be numbers in here, but it's fine. You can just overwrite them. All right, so now I can literally type in exactly what I want. All right, well, I mean, even though we've already done it, we know that I started with -1. Okay, I get 1. Now I can plug in -0.5. Sweet. All right, now I can plug in -0.1. Now I can plug in -0.01. I can plug in 0, that's in the middle of my chart, but that's not shocking. Why do I get an error here? What happens if I plug 0 into this denominator? What's 0 plus 1? Yeah, you're going to end up with 0 in the denominator because 0 plus 1, of course, is 1. The square root of 1 is 1, and 1 minus 1 is 0. We aren't allowed to have zeros in the denominator. Okay, so that's kind of why that happens. All right, but we can go ahead and fill out the rest of it here. All right, so just going across my table, I could put positive 0.01, 0.1, 0.5, 1. Right, and that's how you can get every value in your like on your table very, very quickly. All right, so it's really nice and convenient if you want a bunch of function values. This is a very nice way to do it. Also, a very nice function to know about and skill to have when you take the SAT or ACT for time purposes, right? If you ever want to get a function value really quick or multiple function values really quick, this can help you do it. All right, so, and usually on SAT, ACT, time is kind of usually one's kind of biggest adversary in that test, not necessarily difficulty. All right, so now we can go ahead and just put all of this in here. All right, yeah, that's not going to be big enough. All right, so we've got 1.94, we can say 9. So 1.949. We know that this is, it says error. I'll write undefined because we have 0 in the denominator. -0.01, 1.995. So 1.995. All right, at 0.01, we get 2.005. All right, at 0.01, we get 2.049. And at 1/2, we get 2.225. Okay. So now, again, going back to that definition of a limit, I said, okay, as x approaches some value c, which in this case my c is 0, right? So as my x approaches c from both sides, if my f of x or if my y approaches some value L, then that is, we say, what the limit is, okay? So as my x is getting close to 0 from the left, what does my y value appear to be getting closer and closer to? 2, yeah. So this is approaching 2. All right, as my x's get closer to 0 from the right, all right, what do my y values appear to be getting closer and closer to? 2, all right? Since these values are the same, we can then say that this limit, this overall limit, as x approaches 0 of my function f of x, it is equal to 2. That's it.
So how is the right side approaching?
Well, because we started out here at 2.414, 2.225, 2.2049, 2.005. See how it keeps getting closer and closer to 2?
So are you taking it from 1 down? Because if you go...
Yes. As we approach my C, this is my C.
Okay.
That's why we put that in the middle, right? Because remember, we have to approach it from both sides.
Okay.
So that's why I went, basically what is to the right of 0 on the number line and what is to the left of 0 on a number line, because we had to approach it from both sides. Make sense? So as my x approaches 0, and that number is always going to be this right here in my notation. See how it says the limit as x approaches 0? That's what I know what I'm trying to approach, and that's how I decide what goes in the middle. Fair enough? Okay. Okay. So estimate the value of the limit using both a graph and a table. All right. So first, I want you guys to just take a minute to try to do this with a graph, just like we just did. Okay. And I'll kind of help to get you started a little bit here. Again, give us some room up here. All right, so if I have my x and our f of x, all right, what is x approaching again? 1, right? That tells us right here. So I can put 1 in the middle. Right? What is just to the left of 1? 0. If I want to get closer, I could say 1/2. Right? If I want to get closer yet, I could say 0.9. And closer still, 0.99. What is just to the right of 1 on a number line? 2. All right, so what is a little bit closer to 1? 1.5, right, because we're trying to get closer to 1. What's closer still? 1.1. And what's even closer yet? 1.01 maybe. Okay, so we do have to kind of be careful about what it means to be getting closer to my value, right? So with that in mind, if you need calculators, feel free to come up here and grab one. It's definitely beneficial to practice using that kind of nifty technique. If any of them are not working and or need batteries, I have plenty of extra batteries here. Anybody need batteries? And
How do you clear? What's the command that you clear behind?
second plus 712. She wanted to just wipe the memory to start from scratch. Alpha, y equals enter.
Oh, wait.
Mm-hmm.
Wait. Can we get to like the X thing?
You hit second window, And then go down to independent.
How do you put it all over?
At the beginning, you want to do alpha y equals enter. Or you can be really, really good with parentheses. When I was in high school, we had fancy calculators like these. They just didn't have that like nice fraction command and some of the finer details. So you had to be really, really good with fractions when I was in high school. No, I don't think so. Alpha y equals enter is the fraction command. Alpha y equals enter.
It goes from 125 to negative.
I never had that. I like it. Every time I need it, I definitely go in something else. Yeah. Like, wait.
No, that's not what I meant to do.
Zero. Plug it like that. Sweet. What? Plug it like that.
Oh, I put it
One. Okay.
Well, I didn't.
They got messed up.
I did. Oh shoot, you did something else.
I got one. You couldn't go above. I can get an error. No, I wasn't doing the table. That's not what I was doing. How do you do that? My wife was Wait, just a second. Yeah, I can give you one. Okay.
So you can only enter a certain amount of points.
Yes, but you can always rewrite, like write over top of them. So like as you write them down in your table, you can just kind of keep overwriting them.
What's the difference between like a limit and an asymptote?
We'll get to that actually. Asymptotes are also based off of limits, and we'll get to why that is. Not today, but tomorrow or Wednesday. Ooh, the hiccups are the worst.
One of those things that makes me angry for no reason.
Right.
Especially like if it's after you enter and like it's just nonstop and you're like so full and you're just,
Agreed.
It's a parabola.
Okay. So let's go ahead and kind of take a look at this. Well, you can just work along with me. All right, so we plug our function in. So we have x cubed minus x squared plus x minus 1 all over x minus 1. All right, so now if we go back to our table here, all right, and I doubt yours guys were doing this, but if you have your own calculator and you have one of the newer ones, some of them kind of might be giving you these funky, like, fractions instead of decimals. Sometimes fractions are more useful, right? Sometimes decimals are more useful. Typically, when you're doing limits, decimals are more useful because it's easier to see the number that it's approaching. All right. So a way that you can kind of force that is if you go here to mode, and then down here where it says answers, if you go over to DEC, that'll force all answers to be decimal. All right. Whoops. All right. So, of course, now we're not approaching 0. This time we're approaching 1. So we started at 0 and wanted to get closer to 1, closer to 1, closer to 1. Of course, if we plug in 1, we're going to get an error. That's typically why we're using a limit. All right. And then coming from the other side, right, we would say, okay, we'll start at 2, and then we'll get closer to 1, and then we will get closer yet to 1, and even closer still. Okay, so that should kind of be what our table looks like. Okay, so instead of coming back here and filling in this table, I'm just going to refer to this table since it's exactly the same. Okay, so here, remember my x that I'm approaching is 1. So as my x value approaches 1 from the left-hand side, and when we say left-hand side, we mean speaking in terms of a number line, right, coming from the left. All right, so as my x approaches 1 from the left, all right, what does my y value appear to get closer and closer to? 2, again, right? What about as I started 2 from the right and keep getting closer and closer to 1? What do I get really close to? 2. All right, guys, and if you're ever not sure, just keep getting closer, right? What about 0.999? Right? What about 0.9999? Right? So you can keep, going closer and closer. You don't have to stop at a certain point. So if you're ever doing this on an assignment, Delta Math or a test or whatever, and you're not sure, just keep going. Yeah. Right. Gotcha. Yeah. So just keep going, right? And
when you go to 0.999, why does it go past 2? It's under 2.
Well, remember, as we are approaching from 0, it's always under 2. It's just getting closer and closer to 2. Right? But if I were coming from the other side, see how we started here at 5 and then 3.2, 2.21, so if I went closer from this way, right? So if I did 1.001, I would be getting closer to 2, but from the higher side.
Okay.
Does that make sense?
Yeah.
Okay. And that's fairly common. Typically, when you come from one side, you'll approach a number from either the low or the high side. And then as you come from the other side, you approach it from the other. Does that make sense? Okay. Of course, here on this chart, when I just added values, it didn't put them in the proper place that we would have wanted them on a chart, on a table. Yes?
What happens, on those math, I saw that it had a negative or positive increment. What do you do with that? Is it?
I mean, that's okay. What
does it mean? It has the number, and then in the exponent it'll have negative or positive. That's what
we'll get there. You're jumping way ahead.
I just wanted to see what.
Yeah, we'll get there. We're not even going to get there today. We'll look at that tomorrow. Those are called one-sided limits. Yeah. They're really easy. And they're really easy. It's just, I mean, basically what we just did were two one-sided limits, right? When it has the little negative, that means you're coming from the left-hand side. Only from the left-hand side. You don't care about the other side. And if it has the plus after it, that means you're coming from the right-hand side. That's it. So we just did two one-sided limits, right? We just did one from the left and one from the right. We just did them both at the same time instead of only looking at one. Cool beans. You often, one-sided limits are really, oftentimes they're only useful as when you pick an x as you're approaching a vertical asymptote. Okay. So we'll talk about that a little bit later. Okay. So of course, since as we got closer to 1 from the left, my y value approached 2, and as we got closer to 1 from the right, my y value approached 2. Since these are equal, then we can say that my limit is 2. Okay. Oh, actually, in the directions of this, it did actually also ask us to look at this graphically. Okay, so we already have it in our y equals, so let's just go ahead and look at this graph. Okay, so this is kind of what this thing looks like. All right, it's a parabola. You'll see later that actually this would be a parabola with a hole in it. You guys remember graphing things with holes in it last year when you did rational functions? Some people say no. Well, we're going to be doing that next unit, which is actually why I like to do this unit first. This fits very well into graphs of rational functions. It can help us with those quite a bit. So that's why I like to do this unit much earlier than Horry County Schools tells me I should. Okay, so we are looking as x approaches 1, correct? All right, so we can actually zoom in because we don't really care about some of this other stuff. So I'm just going to move to where my x is 1. So zoom in, boom. All right, so here, and I'll get this cursor out of the way just for viewing purposes. All right, so here, all right, is where my x is equal to 1, right? Like right in here. All right, so basically to look at something graphically, like if I want to look at it from the left-hand side, I just move my finger anywhere to the left of where I'm trying to look, right? And I trace the graph. Okay, as my x coordinate, and in fact, we can just do that here because this will give us a nice visual. All right, so pretend like this is my finger, and this gives me the coordinates that I'm at, right? As my x coordinate gets closer to 1, all right, what does my y value get closer to? 2, yeah. And then we can do it from the right-hand side too, right? I start way over here somewhere, and I say, okay, as my x coordinate gets closer and closer to 1, what does my y value get closer to? 2. All right, so that's why my limit is 2. Okay, so estimate the value of the limit using both a graph and a table. All right, so it's really hard to graph this in a calculator. Right? You can if you really know your stuff. I would guess that 0 people in this class know how to. All right, so it's not really worth going over how to graph, piecewise functions in your calculator, really. It's honestly just as easy, if not easier, to do it by hand. So let's look at, let me get a blank graph here. All right, so let's move this stuff up to give us some room. All right, let's put a grid on here somewhere for us. All right, and we did some graphing of piecewise functions last unit. So remember, of course, 3 is kind of where this graph is going to be broken up. So I'll put my dashed line here as kind of a guideline. All right. So I'll do this point. It's actually not a point, right? It's going to be a horizontal line, all right, everywhere except where x equals 3. All right, so basically, I'm going to have an open circle here, and then I'm going to have a horizontal line in both directions. All right, and then this piece here is just a point, the point 3, 0. All right, so that's what this graph is going to look like. All right, now remember, the key thing about a limit, right, is it says as x approaches some c, right, in this case, it's going to be 3, right, as x approaches 3, but we never ever get there, right, and that's the kind of the key thing to remember here, all right. So if I were to put my finger on this piece of the line to the left of where I'm approaching, right, as my x coordinate gets closer and closer to 3, but remember, I never actually get there, what is my y value? 2. And as I approach from the right-hand side, as my x value gets closer and closer to 3, what is my y value? 2. All right. It doesn't matter that f of 2 is 0. It doesn't matter as far as the limit is concerned. We don't say that this limit is equal to 0, right? Because the whole idea of a limit is that I never actually get there. I can get unbelievably close, right? I can get to 2.99999999999, right? But I'm never actually going to get to 3. And a lot of students make the mistake of, oh, well, it tells me when x is 3, y is 0. So this limit must be 0. No, all right, it's not, because the idea of a limit is that we don't ever get there. Okay, so we would actually say that this limit, as x approaches 3 of my function f of x, it's actually equal to 2, because that's what my y value is as I get very, very close to 3. All right, now it says to also do it using a table. A table isn't very fun at all in this case, but we'll look at it just for fun. All right, so if I'm approaching 3, right, see, and this is where the table is kind of what usually messes people up, because we know when x is 3, y is actually 0, right? But we just have to remember we're never actually getting there. So, you know, maybe I do 2, 2.5, 2.9, 2.99. All right, well, it says that whenever x is not 3, so it doesn't matter what my x is as long as it's not 3, my y value is 2. Well, this isn't 3, this isn't 3, this isn't 3, this isn't 3, right? So we know that I never actually get here, so I don't even care about that value. As I get really, really, really close to 3, what is my y value? 2. Right, and the same thing would happen from this direction, of course, as well. All right, and it doesn't matter how close I get, right? 2.99, 2.999, 2.9999. It doesn't matter. We're always going to be at 2.
What about the point?
Well, it matters for this graph, but as far as for the limit, it doesn't matter at all. Because, again, the whole idea of a limit is that we will never, ever actually get to 3. And the only way that this point matters is if x is 3. But we're never actually going to get there with a limit. Fair enough? Okay. Okay. So estimate the value of the limit using both a graph and a table. All right. So here we have the absolute value of x over x. All right, so again, the table is not all that interesting here. The graph is a little bit more so. All right, so let's just kind of come up with a graph here. All right, so let's just start picking values. All right, well, we know we can't plug 0 into this. Why? Yeah, we can't have a 0 in the denominator, right? And if I plug 0 in for x, of course, I get 0 in the denominator. All right, so let's just pick some values to the left of 0. All right, now, especially looking at a graph like this, right, it's kind of more difficult than a table to start at -1 and go to -0.5 and go to because then we'd only be looking in this very minuscule little box here, which isn't very interesting. All right, so let's start way out here. Let's do -10. All right, well, what's the absolute value of -10? 10. And what's 10 over -10? -1. So at -10, I have the point -1. What about at -9? -1 again, right? Because I'd get 9 over -9. Is that going to happen with any negative number? Absolutely, right? Any negative number I put in there, because any number divided by itself is 1. And then, of course, the absolute value in the numerator will make that negative number positive, but it will stay negative in the denominator. So a positive divided by a negative is a negative, and any number over itself is 1. So that's why any negative number we want is going to be -1. Right? Even all the way up to 0. I can't plug in 0, but I can plug in -0.00000001, right? And of course, then I'm still going to get -1, because I'll get positive 0.00001 over -0.00001, which is still going to end up being -1. Okay, so it's just going to be a horizontal line right here. What happens when I plug in any positive number? Right, well, what if I use 10? What's the absolute value of 10? 10, and 10 over 10 is +1, right? So, of course, using the same logic, anytime I plug in any positive number, no matter what it is, I'm going to get what? 1, yeah. And again, all the way up to 0, but not including 0. Right, again, I could do 0.00001, and that divided by itself is still just going to be 1. Okay. So, as I approach 0, as my x approaches 0 from the left, what is my y value? -1. And as I approach 0 from the right, what is my y value? 1. Do those values match? No. Okay. When those values do not match, we say the limit does not exist. Did anybody get that reference? None of you have seen Mean Girls? God. Really disappointed in all of you. Yes. Yeah. No, I'd probably get fired if I made that your homework, because it's not really school appropriate. So, although there is significant limit stuff in there, she takes calculus and is really not very good at it. But
Which girl takes calculus?
I don't remember the names. Yeah. You're right.
Never seen that. Is that?
I honestly have never seen it either. But one of my classes years ago, like, made me watch like that part, like, the limit does not exist. So now I always say it like that. Okay, so yes, if the limit from the left and the limit from the right do not match, then we say the limit does not exist. Okay, so now we're going to look at this one. All right, and just to kind of cheat, all right, we're just going to look at this graphically. We can easily graph this in our graphing calculator. So just 1 over x squared Right? And we look at a graph of this thing, right? And we're doing, of course, as x approaches 0, right? So as x approaches 0 here, right? And we're actually zoomed in sufficiently. All right, what does it look like happens as my x gets closer and closer to 0? Say that again. The y value increases. Is it ever going to stop increasing? No. All right. And in fact, I kind of like looking at this through a table. All right. So if I'm going to get closer and closer to 0 from the left, right, I can start at -1. Right. Then I can go -0.5, -0.1, -0.01, -0.001. Do we know what E6 means in calculator speak? It's the calculator's way of writing scientific notation. Okay. So the E actually means times 10 to the blank power. That E stands for exponent. All right. So times 10 to the, this is the exponent. All right. So this is 1 times 10 to the 6th power, which is a million. Okay. That's what a million is. All right. So if we do it again, -0.0001, boom. All right. Now we're at 100 million. All right. -0.00001. Now we're at 10 billion. All right. This will never stop. All right. It will increase forever and ever and ever. Okay. Now, what about from the other side? Okay, well, let's come from +1 and get closer. So 0.5, 0.1, 0.01, 0.001, right? It's going to be the exact same, of course, because the denominator is x squared. Of course, when you square a negative number, you get a positive, and when you square a positive number, you get a positive. So it doesn't matter whether that value is negative or positive. It's always going to be the same. All right, so this is going to increase forever as well. All right, now a limit is just that, right? There has to be some stopping point, right? Like, have you ever been driving somewhere and you just see speed limit, infinity? No, right? Because then there is no limit, right? That's kind of the whole point, right? That would be a disaster. There are actually states that have places with no speed limits. Montana is one.
Doesn't they call it an autobahn?
Well, that's in Germany. Yes. But in a lot of Western states where you just have flat nothingness for infinite miles, right? Like you don't get pulled over for going too fast anyway. You can get pulled over for something else, but like you can't get a speeding ticket because there's no speed limit. But like I was driving in Montana once and it said speed limit, be safe.
Oh.
Okay. Yes.
So my grandparents did a trip around the entire 50 states,
Mhm.
and they said that they were so happy that there was no one around them because they just put the pedal down.
Oh yeah, absolutely. Yeah, and you can. Yeah, it's pretty cool. Yeah. Well, there's a lot of states like that, especially out west, like where there's just flat nothingness for hundreds and hundreds of miles. So.
Yeah, my luck there being like something in the road all of a sudden.
All right. So anyway, going back to this, right? We know that the limit as we come from the left, it just keeps getting higher and higher, and the limit as we come from the right, the number keeps getting higher and higher. So it doesn't approach a specific value. Okay, and infinity is not an actual number. Okay, infinity is an idea, right? Infinity is that the numbers never end, right? You can just keep going and going forever. All right, so thinking of it in terms of that, again, we say this limit does not exist, right? There is no bar that I can kind of set on that graph that graph will never cross, right? Because it just goes up forever and ever and ever. So there is no limit. So we say the limit does not exist. All right. And this next one is kind of the craziest. All right. So estimate the value of the limit using both a graph and a table. All right. We haven't gotten to the trig functions yet. We will. All right. But this is the only way to kind of demonstrate what I would like to demonstrate here. All right. So let's go ahead and look at a graph of this. So if we go to y equals, and we go to the sine of 1 over x. And now we'll get to this later, but in order to graph these properly, we need to be in radian mode, but we are, so that works well. All right, so if we graph, yeah, it looks crazy. Yes, it will. All right, but let's just zoom in and see what this looks like. All right, and zoom in again. Whoops. All right, so that's kind of what happens. And the more we zoom in, the more you see this craziness. All right, so let's look at this as a table again, right? So if we go to this table, right, and we're trying to approach 0, all right, so bam, bam. Okay, well, we start here, negative 0.8, negative 0.9. Positive 0.8, positive 0.9. Negative 0.5, negative 0.5, positive 0.8, positive 0.3, right? Let's keep going here. So 0.0001, 0.00001, 0.123451, 0.123456, 0.12345671, 0.12345678, 1. All right. So
There's no way it can exist.
and you're right, it does not exist, right? And it's because it just keeps bouncing all over the place, right? In order for a limit to exist, you have to kind of zero in on a particular number, right? You have to keep getting closer and closer to a particular number. Here, we don't keep getting closer and closer to everything. In fact, if you keep going, this will constantly bounce back and forth between negatives and positives, right? Always, all right? So we again say that this limit does not exist. The limit does not exist.
So the way to determine if it does not exist is if it's like bouncing everywhere and it doesn't look like it's there.
That's one of the cases when a limit does not exist. In fact, we're going to talk about all of them right now. We've already talked about all of them. Okay, we just did examples of all three. All right. So the limit of f of x as x approaches c does not exist under any of the following conditions. Okay. So who remembers the first one that we saw, the first example where the limit did not exist? Exactly. All right. So we say when the limit from the left and the limit from the right do not match. Bless you. Who remembers the second example we looked at where the limit did not exist? Yeah. All right. So we say when f of x increases or decreases without bound, that means that it just goes to positive or negative infinity. And of course, the last example we looked at, what did our f of x do? What did our y values do? Yeah, they bounced all over the place, right? Right. And the mathematical term for that, when f of x oscillates indefinitely. Yes, oscillates. Oscillate means to bounce. Yes.
Is that will not remember that?
Yes, oscillate means to bounce.
You scared me with the word over here.
I hope I spelled that correctly, by the way. It may only have one L. I don't know. Right, there you go. However you can remember. That one, honestly, you'll almost never see. You only see it with funky trig functions like that.
So if it has a trig function in it, is it automatically?
No, not always. In fact, if the argument weren't 1 over x, like if it were just x, that'd be fine. We would have been perfectly fine.
Going to say yes.
No, actually, you're probably glad that I didn't say yes, because that would mean that trig functions would be much more complex than they really are. And you would have had to have learned all of that stuff. I love your mask, by the way. I'm a big Ninja Turtle fan.
You should see my phone.
Nice. All right. Okay. So now we're going to get to the easiest part of the day. All right. Yes, literally the go-to, the first thing that you always want to try with limits is called direct substitution. Okay. That literally means you take whatever the c is, like whatever x is approaching, and you plug it in. And if you don't get any problems, like if you just get a value, right, with a lot of the ones that we've looked at earlier today, you would get 0 in a denominator or, just something that kind of messes us up, right? But if you just can plug it in and you get a value, that's what your limit's going to be, right? So if I plug 4 in here, what do I get? Yeah, that's tough. If I plug 4 into here, what do I get? Pretty hard. Yeah. That's why I said this is the easiest. Like when you get 0 in a denominator or a negative under a square root or something like that. Yeah.
So pretty much whenever x is going to equal 0.
What's that? Yes, you may. Not necessarily, right? X can approach 0. Like if x approached 0 here, would I be allowed to plug it in right here? What's 0 squared? Yeah, see, that's perfectly fine. Now, for instance, here on number 6, would I be allowed to plug in -3? No, right? So if x approached -3, if x was approaching -3, that would be a scenario where we couldn't use direct substitution because that would give us a 0 in the denominator. We're not allowed to have that. Okay, so that's kind of where we have to do other things. But your go-to always is direct substitution. So what's the square root of 9?
3.
Bam. What's 3 plus 4 quantity squared? 49. Bam.
Is that for 5 and 6? Is that -1?
Yes. Yes.
Can you keep this up here so we can read this?
For a small fee of $9.99
No.
per person.
We don't even have money on
I take Venmo,
You're fucking-
PayPal.
Nah, that's my mom. My mom's
Well, you take hard work and dedication.
All right, maybe I might settle for that.
Do you take me paying attention to this?
I actually might take payment in the form of actually doing work. Yes.
I do.
All right. So of course 5. If we plug -1 in there, what do we get? Nope. I know why you said that. What's -1 squared? +1. So what's 1 plus -1? 0. And then 0 minus 6 is -6. Yeah. Easy mistake to make, though. And what's number 6? Yeah, -3. And it's -3, of course, because the numerator is exactly what we just did, right? So the numerator is -6, and then -1 plus 3 is 2. -6 divided by 2 is -3.
Incredible. It's the hardest thing I've ever done.
Right? Super duper
I always
hard.
thought limits were like this super difficult thing.
So yeah, a lot of times they aren't. They can get complicated, and when you get to calculus and you dive into it a lot deeper, you'll get into a lot more complicated ones.
It's really wild. Like, he went over them briefly at the end of the year.
Mhm.
I mean, he only went over like his X purchase negative.
Right, and that's just kind of that's in behavior in terms of limits.
Yeah.
Right. Yeah. Okay. So now we'll talk about limit properties. All right. Also, much easier than they seem. All right. So given the limit as x approaches c of f of x is equal to 5, and that the limit as x approaches some c of g of x is equal to -4, find the following. The first one would absolutely just be 10.
And so this,
All right. Because we know that the limit as x approaches c of f of x is 5. Well, if we multiply that by 2, we just get 10.
it's kind of like
Yeah, kind of. It's similar. Whoops.
so that means the next one would be 9.
And that would be 5 minus -4 would definitely be 9.
That's not horrible.
No, pretty easy. 16. Yep. We like these. You want like 37 of these on your test?
Yeah,
Yeah.
that could be the whole test.
Between this and the last set of problems, just boom.
I would do
Yeah. Square root of 5. You would just leave that one at square root 5, right?
Yep.
And then -16, I think.
-60. I like it. Yeah.
And 15 over -15 over 8.
Uh,
Or 16, -15.
yes. -15/16.
Amazing. Love it.
Right?
Love to see it, huh?
We like that stuff. Good times had by somebody. Actually,
Somewhere.
as far as math is concerned, good times were just had right here. This is as good a times as you can get in math. Super easy. Is Anna making it harder than it needs to be?
Well, I was like talking to Kendall, and the next thing I know, we're on question number 4, and I'm like, whoa, wait a minute. When do we get here?
And you told me that you were going to pay me by paying attention. And instead, you were talking.
Hey, I got to the last slide. I
Your
was
free trial. That was your free trial.
Okay, so we're just going to look at this real quick and then we'll be done. All right. So here's a graph. All right, it says use this graph of the function f to decide whether the value of the given quantity exists. If it does, find it. If not, explain why. Okay, so f of 0 is just a function value. When x is equal to 0, what is my y? 1, yeah. because the closed circle here, right? We know that that is included right there. All right, now, what about the limit as x approaches 0? All right, well here, as my x coordinate gets closer and closer to 0, what does my y coordinate get closer to? 4. All right, and as my x coordinate gets closer to 0 from the right, what does my y coordinate get closer to? 1. So since those two values don't match, what do we say about the limit? Does not exist. All right, and where it says explain why, because the limit from the left and the limit from the right don't match.
Can we say reason 1?
Right, reason 1. All right, so f of 2, when x is 2, what is my y?
Well, it's not 3.
It's not 3 because this is an open circle. Yeah, there is. It's undefined. Right, there is no function value there. Okay, what about the limit as x approaches 2? Well, as my x coordinate gets closer to 2, what does my y coordinate get close to? 3. And as I approach it from the right, what does my y value get close to? 3. All right. So basically, the point of this little exercise was to show you that just because there's a function value does not mean that there has to be a limit. And just because there is no function value, it doesn't mean that there's not a limit, right? One is not dependent on the other at all. Okay. Oftentimes they do match, right? And that's kind of the whole case with direct substitution, right? When you can do direct substitution, that's when a function value and the limit will match. Okay. But they don't have to at all. They do not have to match. Okay. So that is the end for today. All right. Your homework is on Delta Math. There will be a couple of them that you won't be able to do, but remember, of course, your Delta Math isn't due until Sunday. So you'll have do the ones that were kind of covered by what we've done today, especially like the ones that Anna brought up about with the little plus and minus afterwards. We'll get to that tomorrow. Okay.
Good. Oh,